Thank you, Bob. There are 2 or 3 seats up here if you'd like to come in and sit down before we start again. I'm sure you've noticed that the speakers at this symposium are talking in order of alphabet. This means that the order, alphabetical names, doesn't bear any relationship to the time that the person won the Kendall Award. The most recent 2 speakers that we've listened to were Kendall laureates in 1965 and 1966. Our next speaker won the award just last year, and it's interesting that his title for today is exactly the same as his title for the Kendall Award lecture, Surface Electrochemistry. All right, Hubbard, I think most of what you talked about when you won the award probably came from UC Santa Barbara, and maybe a lot of it today comes from Cincinnati, but you'll have to illuminate us on that. Art Hubbard.
My appreciation to Tom Ford and to Carol Micels for conceiving of and implementing this interesting and enjoyable symposium. And thanks also to Bob Hansen for talking about the isotherm developed by Alexander Frumkin for many years, the director of the Soviet Institute of Electrochemistry, whose work on adsorption at electrodes was an important part of the foundation for the work that I'm trying to do this week. Namely, to prepare some well-characterized electrode surfaces as supports for electrolysis, to attach molecules or allow them to attach themselves to the surfaces, to characterize them as to structure and composition and molecular properties, for example, by surface spectroscopic techniques, and then to carry out electrolysis of the molecules while they're tethered or adsorbed to the surface. To do this, one needs an apparatus that incorporates some of the features of surface analysis systems, the alphabet soup to which several speakers have referred earlier, particularly Keith Hall, and then what electrochemistry or vapor phase chemistry over here, some spectroscopic techniques that work well at atmospheric pressure, and then back in for more characterization. Now, the lure or the trap, as the case may be, that got me into this area was the possibility of knowing the structure of the electrode surface and knowing that it was clean as a starting point for electrochemistry. And to some extent that was rewarded, but it turns out that was not necessarily the main event. The rewards of having that well-characterized surface are that we are noticing that electrode surface structure strongly influences the structure of what's on the surface. Adsorbed solvent layers, for example, ionic layers, electrodeposited layers or films, the molecular species and intermediates. And those in turn determine the electrode reaction kinetics of the macroscopic electrolysis that one easily observes. In other words, there's a microscopic aspect of it and a macroscopic, as we've heard earlier today. and it operates with remarkable parallels in electrochemistry. But perhaps the most useful thing about combining surface characterization in vacuum with electrochemistry at ambient pressure will probably turn out to be the fact that there's a sort of a diagonal matrix of techniques and of capabilities that go along with characterization of the surface. The techniques, for instance, like lead that are neat for making well-defined electrode surfaces are also very important for monitoring the symmetry and, in favorable cases, the structure of the species that are formed on the electrode surface as a result of electrolysis. So we discovered a case, and I think in which fringe benefits might have been more important than the original objective. Now, I'll narrow this down somewhat, and if to respond to Tom's question at the beginning, if we think of these 4 topics as being the first 4 years at the University of Cincinnati, then we'll be reasonably accurate. And we approach them really from the point of view of elemental composition, and then electrocatalytic reactivity, and then in the 3rd year at Cincinnati, a big emphasis in our group on molecular constitution of electrode surfaces, and then in the past year or so, crystal and molecular structure. Now, I don't represent these, of course, as the topics to end all, but these are the first 4 that I've had a chance to get around to. One of the things that we've begun to notice during these 4 years, recent 4 years, is that the various categories of particles that one can find on an electrode surface, the atoms, the ions, the molecules, and so on, are remarkably stable in vacuum. That is, if they're chemisorbed, they're a little like the hydrogens on a benzene. And when you distill benzene, a few of the hydrogens come off, but most of the, that's a few molecules out of Avogadro's number. And the overwhelming observation is that the benzene molecule is stable because of the chemical bonds that hold it together. And the surface is stable for that same reason. And in fact, ultra-high vacuum turns out to be a very mild reagent in handling and processing an electrode surface. So even though at first glance it might seem that everything will come unglued when you try to study an electrode in vacuum, in practice, the chemically bonded species, and as I'll show in a moment, some of the electrostatically held species are very stable in vacuum at open circuit at room temperature. Now, in order to get a handle on that experimentally, we used this apparatus. We hooked our electrode surface up to a microammeter. We measured its electrode potential with respect to a stable reference electrode and circuitry. And we controlled its potential while measuring the current, of course, by means of an auxiliary electrode and circuitry. Scanned the potential much as you would scan the energy of a spectrum, starting from the open circuit value and scanning, in this case, positive to oxidize the absorbed species, and then negative again. Now the solid curve is for 3-pyridyl hydroquinone absorbed on platinum 111, in which the scan was run immediately after absorption of the molecule from solution, aqueous solution. The dotted curve is the same experiment, but repeated after characterization of the absorbed molecule in vacuum for about an hour. And you notice there really isn't too much difference between the 2 scans, just a little decrease in the background current over here. In other words, the species are stable to the extent that they remain on the surface in about the same amount, and they retain their electrochemical reactivity in solution. And we've gone on to study dozens, if not now hundreds, of molecular substances, all of which have this characteristic. And it's an easy characteristic to note because we're performing the electrochemistry of each of the species as we go along. A variation on this is a molecule that attaches with a ring parallel to the surface When we scan it before or after vacuum, you get a solid or a dotted curve, which are virtually indistinguishable. The dashed curve is the clean surface itself. Now this, of course, is an irreversible oxidation that converts hydroquinone to CO2. Now, most of you are familiar with the techniques in which a surface is stimulated with an electron beam, and the emitted electrons are energy analyzed and amplified to yield a set of Auger data. The ascending curve being the Auger signal for carbon due to absorption of an organic molecule, nicotinic acid, as a function of the solution concentration of nicotinic acid. And as we increase those orders of magnitude, the packing density builds up. The platinum signal, on the other hand, declines because the increasing coverage of the adsorbed molecule blocks the platinum Auger signal on its way to the detector. So you have a sort of a Beer's law measure of the packing density in terms of the attenuation of the substrate signal. Now, a simple algebraic equation relates the molecules or moles per unit area to the Auger signal, and for convenience we normalize by the Auger signal due to the clean platinum 111 substrate, thereby factoring out the contributions due to the spectrometer itself. And then there's about a 15% correction of the signal to allow for the fact that the atoms in the adsorbed molecule lying between an emitting atom and the detector scatter some of the Auger electrons before they can reach the detector. And this is a somewhat circular, but also you can think of it as an iterative procedure in which one iterates over that 15% of self-consistency. And one can check the self-consistency by looking at the attenuation of the substrate signal by the adsorbed layer and making sure that both sets of data and both sets of equations give a self-consistent result. And one is sort of duty-bound to publish those which do and those which don't. In the case of nicotinic acid, which is typical of the ones which we've studied, there are regions where the agreement is less than perfect and others where it's remarkably good. But in any event, if one is using these data to deduce the shape of the isotherm over 5 orders of magnitude and solution concentration, then one can at least do that at this point. And the uncertainty is of the order of 10% or less. And one can get a first indication of the molecular orientation of nicotinic acid on the surface by building a scale molecular model, measuring the size of the footprint that model casts on the electrode surface, figuratively speaking, and in order to make things work reasonably well, one would postulate, in this case, a slight tilt. In other words, a slight interplay between sigma and pi bonding of this particular pyridine derivative to the surface. And this needs to be investigated by other techniques, and that sort of work is in progress. Having done this, we notice that 150 or 200 aromatic compounds that we study fit into basically 4 categories. Those in which there's some functional group that's responsible for binding of the molecule to the surface, and the aromatic moiety doesn't interact chemically with the surface at all. There are cases such as pyridine in which there's a ring atom which is primarily responsible for attachment. Others in which the ring binds parallel to the surface, or those such as pyridazine in which there are multiple atoms that undergo attachment to the surface. And the isotherms, these were determined by Manuel Soriaga, who's here in the audience today, bear that out. For instance, there's a mercaptan in which there's only one orientation and the packing density is high at virtually any practical concentration. Pardon me. Others in which There's a horizontal orientation at low concentration and a more space-efficient vertical one at higher concentration. Or in a two-ring system in which, one sees both rings parallel to the surface, both rings edgewise, or one edgewise and the other pendant from the surface. And the electrochemistry of this particular pendant hydroquinone is noticeably greater than electrochemical reactivity is noticeably greater than for the corresponding horizontally oriented ring. Now, to summarize the types of molecules we'd like to look at, I've made a very compact slide here. Essentially, we have one or more functional groups interconnected by an aliphatic chain or an aromatic ring or an alicyclic ring. And the functional groups include alcohols, aldehydes, alkanes, alkenes, alkynes, amides, amines, and so forth. And of course, this creates a lot of combinations. We have tried to study them systematically so as to learn as much as we could from them. But one of the students came back from the library one afternoon 4 years ago, the situation probably worse now, pointed out that as best he could estimate, there were 7 million compounds in the categories listed in Beilstein in the categories that I've given here. Now, we're not studying them indiscriminately, I don't believe, but we have well, I'm saying is there's a large variety from which to choose. There are a large number also of substrates that one can study, and we have chosen just a smattering of them as to different structure and chemistry. We've tried to look at some alloys recently and some compounds or compound semiconductors, which are just as easy to study as the platinum 111 surface that I mentioned a moment ago. Now, there's a very intriguing possibility that opens itself up. Since we know the charge to oxidize an absorbed layer electrochemically, that's very easy to measure, and we know the number of molecules per unit area that we started with, and so the ratio in Faraday's law gives us the average number of electrons to oxidize an absorbed molecule. And interesting phenomenon here. A little piece of paper that says Hubbard on it
Has now proceeded to.
has now found its way into the program. Okay. Thank you. Yeah, okay. Now you're going to need to, well, I can do it here, I guess. Having done this for a wide variety of compounds, I've showed us three types, alkenes, alkenoic acids, and alkenols, in which we notice that it's really just the first three carbon atoms, the double bond and the adjacent carbon, that undergo oxidation. And the product contains a carboxylated substituent at the third carbon and makes 2 moles of CO2. And we've gone to the trouble of collecting and chromatographing some of those as well. It's interesting also to monochromate electrons, bounce them off of the surface, and then energy analyze them, and thereby get a surface vibrational spectrum, a technique that we borrowed from the literature of the past 20 years. This slide shows nicotinic acid absorbed on platinum 111, and the upper spectrum is the EEL spectrum. The lower spectrum is merely the gas phase IR spectrum of unabsorbed nicotinic acid. And you notice that the features of the IR spectrum of the parent compound are present under the envelope of the EEL spectrum of the absorbed compound. The only surprise in this, to me anyway, was that is right out here. If I make the electrode potential positive during absorption, the vibration due to the acid OH stretch disappears, suggesting and later confirmed by other techniques that the positive potential causes the carboxylate group to coordinate to the surface along with the pyridine nitrogen. we know it's there because we can titrate it with KOH. For instance, after rinsing the surface at pH 10, the spectrum is now the spectrum of the carboxylic acid salt rather than the free acid. And that situation is summarized here. At negative potentials, a pendant acid group. At positive potentials, bidentate coordination, we can actually see the electrolytic current for interconversion of these two species at the surface. Similar things happen at absorbed layers. Anions like to absorb on platinum much as they do on silver with release of an electron, chalcogenize 2 electrons. But bifunctional absorbates, nicotinic acid that I just showed you being an example, can actually have a residual anionic charge in the pendant part of the molecule. The scans, for instance, in bromide, show a hydrogen region, an anion absorption and desorption region, and an oxide absorption and desorption region. And the isotherms of the type that Frumkin liked to measure bear this out. Notice that bromine goes through a maximum, oxide increases at the positive potentials, and cations at the negative potentials. And these data were measured by Auger spectroscopy. And interestingly enough, the electrochemical features of anion absorption and desorption correlate very nicely with the lead patterns. That is, there are structural transitions which the lead and electrochemistry both pick up. Likewise, there's a pecking order for retention of cations at these anionic layers that tend to vary with the strength of solvation of the ion, the charge of the ion, and its ionic radius. We've looked at a series of electrodeposition situations, a couple of different substrates and a few different deposited metals. And this is, I think, the closing slide, should be the closing slide. And you start at the rest potential in plate silver, and you see a series of structures, monolayer structures, forming as evidenced by lead and by other techniques. The Auger electron angular distributions image these beautifully. You're forming about 2/3 of a monolayer, two monolayers, and then bulk. And you can get much the same thing when you scan back in the positive direction. So once again, these surface structure and composition probes have an intriguing future ahead of them for coupling to characterization of electrode surfaces and electrodeposited layers. And we've just, if you'll pardon the bad pun, scratched the surface in that area as yet. I certainly want to acknowledge those who had the patience and vision to fund this kind of research, and to thank those who did all of the work and most of the thinking. Thank you for your kind attention. And they say any time in a lecture is a good time to stop.